Okay, that's mean welcome again. This is the chapter 5, and chapter 5 is the last part of this class. That means in chapter 5 we will talk about the application of integration, and one of them is finding the areas between two curves. The other one is the volume of the solids. And I will try to cover everything. If the session will be too long, maybe the last section, 5.3, I can cover, I can pre-record and send you a link. But definitely section 5.1 and 5.2 today. Okay, that means areas between two curves. I will my video. Okay, that's what we have to do. We have to find out something like that. If we have two curves, f of x and g of x, and we would like to find the areas between. Of course, we know how to find the area under the curve and bounded by the x-axis is simply actually a definition of the integral. But having two curves is just slightly different, but it's still an integration involved. That's what we will do. Hopefully we remember beginning of chapter 4, the introduction to integrals. In order to approximate the area under the curve, we are using rectangles. That means I will do the same. I will divide my section from A to B and bounded by the pink curve and the blue curve. I will divide it by subintervals, and then I will create the rectangles. We know how to do it. And each of the rectangle has the width, the base, delta x. And what we also need for the area of the rectangle, we need the height. That means now the only thing is we have to find out what is the height of this vertical line. And the length or the height, the length of the vertical line bounded by two curves is simply the top value minus the bottom value. Yeah, that's as simple as it is. Like, let's say if this will be 10 and this will be -3, for example, just numerically, then what we will say, if I will ask you, maybe you can even answer, what is the distance between 10 and -3? Can you type the answer? Distance between 10 and -3. Oh, how many units we have between 10 and -3? 13, yeah, of course. That means we don't even need any special like equation or expression, but mathematically we will say it's the top value, 10 minus -3. 10 minus -3, of course, is 13. That means having a value, f of x and g of x at the bottom, to get the distance, the vertical distance between the top and the bottom, we will take the top value minus the bottom one. That means this is the height of that rectangle. Okay? And now we know the process. The one rectangle, did I type? Okay, that means one rectangle, the area will be delta x times the height, base times the height, base times the height, and height is just the difference. Adding all of them, we will use the sigma notation. This means that we're adding all of them, from the first one to the nth one. And if we want the perfect approximation, n must be infinity. Okay, that means n is infinity, and then it's perfect approximation. And we also recognize a limit of the sigma, limit of the Riemann sum is simply an integral. That means, let's see. Yeah, that's the definition. We have, that means to find the area between two curves, we simply have to integrate, because the limit of the sigma, one more time, is just the integral from a to b. limit of the sigma. That we have to just to integrate the difference between two functions, the top one minus the bottom one. Okay? And that's the f of x must be greater, and from a to b with respect to x. Okay? That means that's quite simple concept. But please remember, we will do some exercise. Yeah, this is application of the integration. Right? That means it's not just integration. Because one thing it's you will probably notice by practicing integral, when we integrating, just simply integrating, we may have the value positive, we may have value negative, we may even have zero. Yeah? Like for example, if I will draw a function just x, you can see I'm trying to draw, and what will be the integral from -2 to +2? Okay? Just the integral. That means who can tell me the answer? What will be the integral if I will just integrate x from -2 to +2? It's zero. Yes, thank you, Taran. Of course it's zero, because we remember is the net area. Everything what is above is positive, everything what is below is negative, because the value of the function is involved is negative, and they are exactly the same amount. It's zero. Okay, that's good answer. However, when I will ask you what is the area bounded by two curves, and one of them will be x, and the other one will be y equals to 0, which is actually the x-axis, then the answer is not 0, because we have to follow this formula, we have to subtract something, and both of them will become positive. That means this is the main mistake, that if we will see something like that, if you will draw it, you will say, oh, the answer is 0. But the answer will be not 0 if I'm looking for the areas. I'm not looking for the net area. I'm not just integrating. I will be applying an integral. But let's see. What I do have just like another explanation that this formula works, because if we will think about an integral just of f of x, which is just the integral from a to b, that means an integral of f of x is simply everything. It's below the pink curve and bounded by the x-axis. And if I will subtract the integral of g of x, which is the blue part, I'm subtracting this, of course, I do have the area between f and g. That means it's just another way to look at this. But I will repeat one more time. If you will have a question, please find the area bounded by two curves. The answer is not negative, and the answer is not 0. Okay, let's see. And I have a first exercise. Find the area of the region bounded by the parabola x squared plus 1, bounded above, actually. Oh, I am nice. I'm telling you which one is above, which one is below. Okay, not always. We will be so lucky. That means bounded above by x squared plus 1, bounded below just by x, and on the side from 0 to 1. And I do have a graph for you. That means that's parabola, x squared plus 1. Of course, I don't need the entire parabola. And that's the line. That's in parabola above, the line below, and the vertical lines 0 and 1. Okay. That means in order to find the area bounded by these two curves, we simply have to subtract the top one minus the bottom one. That means I think I named this one. That means we have F1 and F2, F sub 1, F sub 2. That means this is the top one. We can see top one minus the bottom one. X squared plus 1 minus x. We don't even have to draw this rectangle. I was trying to show a little bit of the definition, but just remember subtracting the curves. And I believe this integral is relatively easy. Integral of x squared, x cubed over 3, integral of 1, x, integral of x, x squared over 2. And substituting 1, we're getting 5 over 6. That's for this, since this application, I'm assuming that we do have enough practice with integration. That means this is important. And if the integral is relatively easy, I will ask for the final answer, but I may only ask you to please set up an integral. That means this is the settings. That's important. All of the positive, negatives, they have to match to the definition. Okay, but let's jump one step above. Okay, find the areas of the region enclosed by parabolas x squared, and the second parabola is 2x minus x squared. Okay, that's what do you think? What is missing in this question? We do have two curves, but something, it looks like it's missing, maybe not. Because we have one parabola, the points, yes, the points like the bounds on the left and on the right-hand side, correct? The A and the B value. Thank you, Taren. Okay, that means if it's missing, probably it's not a mistake, it's just extra job for us to do it. That means what we will do, because we theoretically, we don't even know, I mean, we can draw the parabolas, but we don't know like the position, like one is the x squared above, or maybe 2x minus x squared is above the other one. That's when we have to find a point of intersection of these two curves. Okay? That means points. Actually, we still don't know. I did type this. Let's say we don't know which one is the first one, which one is the greater one. Okay, that means please remember, if the points A and B are missing, we have to find them, and we will call, for now, we will call points of intersection, because we have to know where these curves intersect. So let's see, points of the intersection means that, of course, I name this one X, the first one. I mean, this is the first one, and this is the second one. Okay, that means points of intersection means the first curve must be the same like the second one. X squared equals to 2x minus x squared. I can add all of the terms to the left-hand side, factor out 2x, and I have 0 and 1. 0 and 1, which is actually 0.00 and 1, 1, if I substitute to one of them. Okay, that's me 0.00 and 1, 1. And what I have, I do have the curve, and the graph, the curves looks like that. I know that you will have no problem drawing x squared, the blue one. Okay, this is just x squared parabola. That's simple. I hope you can still draw, you can still find out the position and the location of the parabola 2x minus x squared. Because what we see, to draw the pink one, we see that the leading coefficient is negative x squared. That means we know that parabola will be up and down. And we can also find the zeros of this parabola. We can see factoring out, that's something different than we just did the points of the intersection. This is just drawing the parabola. That means factoring out x, I can see that x is 0 or x is 2. Then I have 0. That means we have 0 and 2. And having the points on the x-axis, I can simply draw the parabola because I know that it's bounded down. It's open down. Okay, and we, of course, we did calculate the point. That means the point of intersection, it's 1. And we can nicely see the yellow part, the golden part, is the region enclosed by these two parabolas. No other one will, the other parts will not even create a closed area. Okay, That means this is the part that we will take care of. In order to find the area, we have the limits of integration from 0 to 1 only, and the top curve minus the bottom. Of course, if we draw properly, we see right away. That means we can see the t, I just name yt, yb, y top and one y bottom. And that's the top function, top parabola, minus the bottom one. That means you can see how important it is, like positive sign, negative sign, like everything is extremely important. Because we can't just say later, oh, it's just the, oh, I made the small mistake, instead of plus, I put minus. No, 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 that's the concept, that's this one. Okay, and I believe I did solve the integral, but as I said, I may only ask you to set up an integral, but let's solve it. Oh, what I did, 2x minus, because we have one x squared and another x squared. That means it's negative 2x squared. Integral of 2x is x squared. Integral of x squared is x cubed over 3, and 2 was the constant. Okay, that's me, no mistake. Substituting 1 and 0, 0 will give me 0. We're getting 1/3. But you can definitely do it. I will box this because I want you to set up correctly. That's the key. Okay, as we can see, it's not complicated. And what we have on this slide, we have one more extra thing, points of intersection, because most likely they will be not given. Okay, let's move on. Okay, that means now I can even show you, don't worry, how important are the points of the intersection. Because the previous question, we were lucky, we only had, I mean, we did have 2 points of the intersection, but we did have like one nice loop, one nice region bounded by 2 curves. But what we may have 2 curves given, and we may even have the A and the B value, like an interval provided. Okay? And now, since we know something about points of the intersection, we theoretically have to always find the points of the intersection, even if the numbers A and B are given. Okay? Because please note what could happen. I may have a points of the intersection which actually fall inside an interval A, from A to B. And if, as soon as we have points of the intersection, the position of the curves changed. One of them was, we can see the pink one was on the top, and then suddenly it's in the bottom. That means having these points of the intersection, the first one, the second one, we have to create 3 different integrals in order to find the area. The pink one minus the blue one from A to x sub 1, and then the blue one minus the pink one between x sub 1 to x sub 2. And the last one from x sub 2 to B, the pink one minus the blue one. Always the top one minus the bottom one. Because if we will just say, oh, g of x minus f of x from A to B, we will get the wrong answer. That means overall, I know that we don't like absolute value notation, but we will say this, that the area between 2 curves, f and g, the area between 2 curves, it's the integral from A to B, and it's the difference, but must be, absolute value must be applied. Taren is asking if this is the net area. Yes, can I say, but no, I can't say, I'm just trying, no, I can't say yes, because the net area could be still negative. Net area is just the special terminology, special name for the integral, definite integral. That means if we remember, the net area could be still negative or could be 0. That means it's not really, no, I think we can't just say, we just have to, always the difference Yes, like, you know, we can't just say, because net area, we're not applying absolute value. That means, no, it's not the same. Yeah, good thinking, but it's not the same. Because applying this, we just want the difference to be positive. That means, let's say if we have, oh, my writing, 3 minus 2. What's the difference between 3 yeah, what is 3 minus 2? Of course, it's 1, right? You don't want to even write. And what is 2 minus 3? Yeah, it's -1. That means that's what we would like to avoid. We don't wanna like subtract something. If I have, let's say, quantity 3 and quantity 2, okay, and if I will ask you, what is the difference between 3 and 2? And everybody will say 1. Yeah? Of course, either way, I don't know if I'm subtracting this way or this way. Everybody will say simply 1. That means that's what we would like to do. The difference is 1. The difference is positive. Okay? That means that's what we're doing. But let's see how can we apply to the question. That means I have nice trigonometric question. Okay? Hopefully we know the curve, sine and cosine. That means will be not a problem. Okay, that means find the area of the region bounded by the curves sine x and cosine x from 0 to pi over 2. That means we know the interval from 0 to pi over 2 and the sine and cosine. And probably you can picture in your mind right now that actually they do intersect between 0 and pi over 2. That means let's try, first of all, to find the point of the points of the intersection, or maybe point. Sine of x must be the same like cosine of x. What I did divide by cosine of x, both sides. Everybody is okay with this? Because looks weird. But when I divide by cosine of x, okay, cosine of x over cosine of x is 1, sine over cosine is tangent. Okay, and now can you tell me tangent x is equal to 1? Then tangent for what angle is equal to 1? Oh, do you know your unit circle? Tangent for what angle is 1? Thank you for typing pi over 4, of course. Excellent, pi over 4. Then let's see, I have the nice graph. Don't worry, it's lots of labels, but you can probably do it. Sine and cosine. And we can see nicely that they definitely intersect. Even if you will start graphing, you will probably figure out that this is in the middle between 0 and 2, pi over 2. Okay, that means they intersect inside the interval. That means they changing the position. We do have 2 parts we have to integrate twice. Or if we notice, the region A sub 1 and the region A sub 2 is exactly the same. That we may use the symmetry. I can integrate and get the value of 1 and multiply by 2. Okay, that means this is just the very, very general settings. Cosine of x minus sine of x, absolute value, from 0 to pi over 2. But now, let's see what I did. I have to split. From 0 to pi over 4, the top curve is cosine minus sine, the bottom one. In addition, from pi over 4 to pi over 2, sine minus cosine. And again, the second line is the really nice settings. But as I mentioned, I can even pick one of them and multiply by 2. That's the symmetry, because they are identical regions. And I pick this one because one of the limit of integration is 0. We like 0. Always is a little bit easier arithmetic. Okay, and I think I did finish this integral. Integral of cosine is sine of x. Integral of sine of x is negative cosine, and I change the sign. And substituting the upper limit, substituting the lower limit. And of course, remember the fundamental theorem of calculus. and sine at 45 and cosine at 45 has the same value. Sine at 0 is 1, cosine at 0 is 1. I mean, cosine at 0 is 0. Did I say 1? Again, sine at 0 is 0. Cosine at 0 is 1. I'm just trying to read this and pointing, because my point was, normally when we have limit of integration 0, we kind of assuming, oh, the computation will be 0. But we do have number different than 0. Okay, that's what I was gonna say. Cosine at 0 is 1, of course. 1. Okay, and then I add them together, minus 1, and we can leave it like that. We don't even have to distribute. Right? But we can see we can't just subtract cosine of x minus sine of x, or the other way. No, because then we will get wrong answer. That means, again, the boxed line is the concept. It's important to know the settings. Okay. What else I have? Let's see, lots of nice examples. Okay. Find the area of the region enclosed by the function y equals to x plus 2, just the line, and then y equals to, actually, root x. X to the 1/2 is the square root of x. And now we do have y equals to 2, the horizontal line, and y equals to 0, another horizontal line, which is the x-axis. As we have so many curves. What I did, I tried actually to draw them. Of course, you probably learned just today that we should start with the points of the intersection, and we will try to compute the points of the intersection. But let's see what I did. Oh yeah, actually I didn't compute, but I just draw y, x. That means I have my line x plus 2. X plus 2 is the linear function with y-intercept 2 and x-intercept negative 2. Square root of x, we know square root of x, looks like that. And then we have a horizontal line 2 and the horizontal line 0. That means is this. This and this. That means this is the region inside here, which is bounded by all of the curves. And this one, of course, I put the labels, but probably we can still, because what was my point? My point was that, for example, we have so many curves, and how can I set up an equation for my points of the intersection? But you will definitely see that the square root of x, this function, is not even intersecting with the line. That means I just want to show you that you may also start this way, especially if they are relatively easy function, because setting up x plus 2 equals square root of x, we will spend time to get the equation, to get the solution, and we will have no solution, because we can see the root function and the linear function, they will never intersect. Okay? But what these functions actually did, they intersect with the horizontal lines. That means that's easy, that's 0, this is negative 2, and this point. Yeah? Of course, the answer is given, but you can probably think square root. Yes, square root of what number will give me 2, because the value was 2. That means you will also know right away. Okay? Or, if you prefer, you can still say square root of x is 2. Yeah. You can square both sides, and it's just 4. Okay? That means that's the way that we can do it. Okay, but now we see also something, yes, something different. Because we see two different, we have one region, but we have kind of two different things. From negative 2 to 0, we have the line on the top. Okay? That means probably I have to set up my integral, which in order to get the area. this line minus the bottom curve. The bottom curve is 0, but I still have to like kind of write it down because I can't miss any sign. And then the second region is this line, which is horizontal, 2 minus the square root of x, right? And I think I put this down. Negative 2 to 0, it's the line minus 0. It's funny, but just in case. And between 0 and 4, I have 2, value 2, the function 2, minus square root of x. And that we can see, that's the way to do it. Also, we have to be careful what is the top functions. Okay, but let me actually stay on this slide, or maybe hang on, do I have, oh yeah, I have another slide. Because what I have to tell you, we do have a little bit different way to do this, because we can see it's not easy. I mean, no, it is easy. It is easy. It's not really like complicated, but it's long, right? We have to like split from two integrals, and I mean, it's still okay, but I can show you something. My next slide has exactly the same, I just copied the same question, the same curves, and I will write down, because what we can do, we can twist a little bit the definition, I mean this application. In order to find the area, instead of looking like at the top function and the bottom, we can try to integrate not with respect to x, we can try to integrate with respect to y. Let's see, the area will be the integral. I can still say maybe from C to D and f of y and f of another y with respect to y. That's mean what we have to do. We have to kind of look, not looking like from the x-axis perspective. We will try to look from the y. Right? That means if I will try to get back to the definition, to the rectangles, we will do this way. Okay? We will do the slicing this way. We will create the rectangles. And in order to find the height of this rectangle, I can maybe build one of them. In order to find the height, I have to find the length of the horizontal line. And the length of the horizontal line is simply the right value minus the left one. Right? We can see. But now, what we have to do, we have to get these equations. We have to solve for x in order to get the y function. That's because everything is in terms of y. That we can see, I will integrate. And this is the nice example because we do have perfectly the right-hand side and the left-hand side curve, and bounded by y0 and y2. That means this will be 0 and this will be 2. Okay, this curve is square root of x. If I will solve for x, it's y squared. Perfect. This one is y, x plus 2, but I need the y expression. I have to solve for x, y minus 2. Okay? From 0 to 2, then, and let me maybe put the, because I want to, that means this one, I will name the right-hand side minus the left-hand side. Okay, that means on the right-hand side, we do have y squared. On the left-hand side, we have y minus 2. Okay, that we can see the right equation, okay, and the left equation, because that's how we can get the distance between the distance of the horizontal line. I can just ask you, then you will. Yeah, for example, something like that. It's no connection to this. How many units we have between -2 and 5? Do you remember? We have 7, of course. But how can I compute this? I can say my right value minus the left value. And as we can see, this is, of course, 7. But mathematically, we have to do this one. The right value minus the left one. The right function minus the left one. That means this is another way to get maybe a little bit faster sometimes. But please remember, if you can still apply the old method. Yeah, but I just wanted to point that this method also exists. Okay, that means let's see my general. Yeah, that means this is something that we will probably see the the right curve and the left hand side curve bounded by C and D, everything in terms of Y. And I have another one. Oh yeah. And then the integral that represents the area will be the right curve minus the left one. But please remember, everything is in terms of Y. Yeah, also nice method, especially if we can see nice, better right and left boundary instead of the top and the bottom. Okay, and I have one more picture. Oh, that's what I was thinking. Yeah, I was just trying to flip this, but we can see. Yeah, I named them like, I put X because we will have to solve, X is equal to the Y formula. That means the right equation minus the left equation, the same thing. I just kind of flip this, but you may ignore it. I know that once one student asked me like, oh, if we will flip it, it's almost like a top minus the bottom. Yeah. If we trying to think about the rectangles, that means this is kind of like the X values, but of course it's the Y and the top and the bottom. But no, we can switch for a moment. We can think right and left. Okay? But it's just the same idea. Okay, and then I think I have here. Okay, I have again. That's what I just wrote for you before, and I did flip it. We don't have to. You can look at, but it's kind of like the top and the bottom. When we switch the location, if you feel more comfortable having an X as a horizontal line. Okay, but that's the way to use a different method. Okay, what else I have? Oh, I did integrate. You can try to integrate and get the value. I don't have all of my steps, but you can try to as a practice. It's, again, all of the resulting integrals, they are relatively easy. Yeah? The settings is crucial because that's the new concept. Okay, let's see, do I have something else? Okay, oh, I do have it. And then we can start maybe volume. That means, let's see what I have. Find the area enclosed by the line, okay, x minus 1, and the parabola, oh, y squared equals to 2x plus 6. That means I'm assuming that this is the function x in terms of y. Yeah, it's the other way. If we will solve for x, we will have, am I right? I'm just trying to subtract 6 and then divide by 2. Okay, that means 1/2 y squared minus 3. First of all, points of the intersection. That means I will name, because of that parabola, I will assume that I'm actually doing not the top and the bottom curves. I'm doing the right and the left. That means let's solve this one for x2. Y plus 1. Okay, that means y plus 1 must be the same like 1/2 y squared minus 3. Okay, we have a quadratic equation. I did multiply by 2 and moved all of the terms to the left hand side. And I have nice, I can factor easily. Y is -2, y is 4. Perfect. And what I have, I do have the graph for you. I make the graph. And let's see. I know that all of my students will have no problem to draw the line. Even if you think y plus 1 or x minus 1, you can definitely draw the line. Now you can see that's, okay, that's parabola. Because what we see, let's look at the top equation. We have 1/2 y squared. That means it's positive leading coefficient. That means parabola will be open to the positive, like in the positive direction. Because I can't really say open up, because now we don't have up and down, we have right and left. That means if the leading coefficient in this reverse equation, it's positive, parabola is open to the right, because that's the positive direction. And -3 is telling me that I have to shift the parabola 3 units down, but down is the negative direction, the left. And that means you can probably draw it. And then you can just draw the parabola. Don't worry for the zeros on the y-axis. We don't probably need them, but we do have nicely, we do compute the x, the points of the intersection. That means this point is 4 and -2. That's what we got. Okay, 4 and -2. Okay, and it's perfect. Now when we have all of these settings, all of the graphs, labels, just to get the area, the right curve minus the left one. And we can see that's the right one, that's the left one, parabola is the left, line is the right, and limits are from -2 to 4. Yes, really nice question. And what I did, I simplify a little bit inside, I integrated, substitute 4, substitute -2, simplify, and get the answer. Of course, I went quite fast, but what is important for me? Let me box it. This. That's the key of this slide. Rest of them, I'm not worried, was chapter 4. You can definitely do it. You can try to cover this solution and try to get 18. I know that you will do it. But please see the settings, the application. And in this case, because do you remember what I just said 5 minutes ago? I think sometimes you can, even if it's longer, you can still try to do it with respect to x, but I don't think we can do this one. Let's see. Yes, I have the graph. Like, can you see, if I would like to divide with respect to x, because that part is weird, I can find this point, no problem. That means I can integrate from that point to this one, which I will have the top and the bottom. The blue part is not problem. But what about the pink part? That's weird, because I have to have the positive part and the negative part of the same curve. That means, how can I say the top curve minus the bottom one? It's the same curve. I mean, you can still do it, but it looks weird. That means from -3 to that point, I will have positive part. And Taren, that's the thing. No, it's not 0. That's what I was saying. Can you see the area, the pink area? I did use a pink ink, if I can say this way. I didn't cover 0 areas, 0 regions. Yeah? You can see, like, if let's say, I don't know, how can I explain? If I have to pay for my ink, I will pay. That means I didn't pay 0. I do have some areas, because it's not just the integration. If we will simply integrate, yes, but we have to apply the integral. Yes, you can say twice, right? Correct. Actually, I like this. You can kind of get the area of this, which will be just the integral, and multiply by 2. Oh yes, then it's correct. But we can see. You have the knowledge, you have the tools, you will probably figure out if, let me change, if you really want to avoid this, because sometimes at first, I know just by experience, some students, they don't like this right, left, but as soon as you do 1, 2 problems, you will like it. You will say, oh, it's much, much easier. Yeah. Hang on, we have another question. If the graph was flipped over the y-axis, would you still do the right left? Oh, no. Oh, no, always right minus left. Okay, whatever, yes, whatever position, whatever, no. We still have to do right and left. Let's see. What I'm looking for. I'm looking for this. Yeah, like if you have to find the distance between -2 and 5, like whatever, I don't know, if I will have, I still have to subtract the right minus left, always. Okay, let me come back. That means yes, please, yes, always, even if it's like a little bit weird position or you think it's like flipped, no, always right minus left or top minus the bottom, but that's relatively easier than this. Okay, good, yes, good questions. Oh, but even yes, if you think you can figure out with respect to x integral, it's still good. But remember, not 0. Okay, and I think, hang on. Okay, I do have one. Another, this is the last question for this section, and I promise I will start the volume, at least 5.2, as I said at the beginning. Okay, find the area of the region enclosed by the function x and x cubed. And okay, I do have some things, but I don't know. Okay, I will maybe erase because I don't have the graph. We know how the function x looks like. That's x, and we know x cubed. Okay, that means, to be honest, if I will see this question, if I will be taking a test, I will start with this. Okay, because I know x cubed, that means looks like that. And I see this is of course 0, and I see this. That means, do you think what will be the points of the intersection? What will be that point? And this one. That means x and x cubed. For what values are they the same? For what x values? What is this point? I think it's 1. Because 1 cube is, it's also 1, x equals to 1. And what about this one in the third quadrant? What do you think? It's -1. You can even, because no other values are not, if x is 2, 2 cube is not the same. If x is like, I don't know, 3 cube is not the same. Okay, that means if you will see, let's say, this question on the test, I don't remember the answer, but do you think the answer is 0? Because if you will see the option A, B, C, D, E, and one of the option will be 0, do you think you can pick the answer 0? Oh, don't be. No, okay, no, because it's, yeah, of course not, no. Yeah, yes, you can use, exactly, Yuktaren, really good, you're using the symmetry, you can do this. That means first of all, we know that they are identical. I don't know if my graph looks like, but they are identical. That means you can simply focus on one of them and multiply by 2. But please remember, it's not 0. You can actually see I did use my blue ink. Okay, that means if somebody will charge me for the amount, I did use something, right? That means I didn't use at all. That means please always think this way, especially if the question is asking for the area. Okay, that's it. Let's see what I have. Points of intersection, and then I did the general settings. Do you see the absolute value? Because between -1 and 1, we have another point of the intersection. And then, what I'm doing? Probably I'm doing 1 and 2. 1 and 2. Okay? Because for the first one, the bottom part, I have x cubed on the top minus line x cubed minus x. from -1 to 0. And from 0 to 1, I have x minus x cubed. But who typed the answer? Taren, you said that we can take the second and multiply by 2. Oh, actually, I didn't finish. Let me write for you. Two times could be solved either way. You can compute each of them and add together. You can compute one of them and multiply by 2. From 0 to 1. I think this one is the second one is, the bottom one is also easy. Okay, that's mean that I didn't compute this. We can probably compute x squared over 2x to the power of 4 over 4. 1/2 minus 1/4. 1/4 times 2. Oh, I almost forgot. Okay, 1/2 is the final answer. Okay, I'm just trying to, you will do it in a second. Okay, that's mean 1/2, 1/4 times 2. Okay, but please remember, not 0, especially with something like that. Okay, okay, really good. You will not miss any of those. And let's see what we have. Okay, I do have multiple choice, but we will not, and can you see we will not solve this? I can leave it for you, but you can see what I'm asking. That's what I was trying. Set up and do not evaluate. Yeah, that's what we can see. It's just settings important. And then this one I ask you to evaluate. This one is just the setup. And the next section. Okay, that means volumes. That's another application of the integrals. Let's see, we do have two methods to compute the volumes. 5.2 is talking about 1 and 5.3, but 5.3 I will put the link separately. Okay, that means let's see, volumes of the solid. First of all, we know, like, we have some intuitive, like, definition in our head, like what volume means, and especially if we talk about the right cylinders. That's when if we have a right cylinder, the right cylinder is not only the middle shape, yeah, because that's what we always think. This one is circular cylinder because the circle is in the bottom. We may have rectangle, we may have a square in the bottom, we may have even weird shape. As soon as we have the same two bases, top and the bottom, we call congruent, and parallel sides. That means the same bases, top and the bottom, parallel, and also, actually, no, I should say perpendicular. The side must be perpendicular to the base. Yeah, this one is obvious. That means the bases are parallel, but the side of the shape is perpendicular. That means that's the cylinder. And now the point is volume. Volume will always have the same formula. The formula of the base times the height. That means whatever the formula of the base is, A times the height. Pi r squared times the height. Length times width times the height. Yeah, we know that, especially this one and this one. We can see they follow the same definition. The area of the base times the height. Okay, that we have no problem if we have this type of shape. Area of the base and the height. We can get the volume. But now the problem is not all of the sides are gonna be nice and straight. That's what we will have. We will have, maybe too much. We will have something like that. Kind of like it is. I hope we can see 3D. It's the 3D shape. We can think that is, I don't know, football, maybe. or I always see, probably I type even somewhere, I always like to think about the loaf of bread. You know, like we have this nice loaf of bread. Not the nice square one. Oh, no. Just the natural loaf of bread. That means now if I slice the bread, oh no, let's wait with the slicing. Let's wait with the slicing. Having this loaf of bread or having this shape, I have to find the volume, okay? That's mean, as I just said, because probably I'm too excited to tell you this, that we can see we can't really, we kind of, if I will cut my bread or if I will cut my football, I can think that I do have the base, like this one is left and right, but I can put in the vertical position and I will have the bottom and the top. That's mean I can kind of see that it is cylinder, but unfortunately this is not really perpendicular, this is bended. That's mean what we will do. You can probably guess that we are applying integrals. Integrals is always adding infinitely many terms of something. That means we will take this and we will try to cut. Like I can tell you mathematically that we will take a plane perpendicular to the x-axis in this case, and I will slice it, okay? And I will try to look what is the cross-sectional area looks like. Okay? Or again, you can imagine that bread, and if you will take a knife and you will slice the bread. Okay? You will slice the bread, you will have lots of slices. Let's see. And each of the slice or each of the piece, I will try to approximate as a cylinder. Okay? Because you can imagine that we're taking this slice of bread and we're putting on the plate. Yeah, and then you have the base, you have two congruent bases, the base, the top and the bottom, and you have the thickness of the slide. Yeah, like we can see, we do have the thickness. That's my slice of bread. I'm gonna eat this. But we do have a thickness, and the thickness will be the height. Yeah, that looks like a cylinder. I have to find, in order to find the volume, I have to find the area of the cross-sectional area and times the height, which will be times the thickness. Okay, let's see. Okay, that means we know the thickness delta x. That's actually kind of the same. The A of x will be the cross-sectional area. But now this one. Can you see this is kind of like our bread? The slices, of course, are too thick. Okay, the slices are too thick, but we know what to do because how many slices I have? 1, 2, 3, 4, 5, 6, 7. That's not good number. We need infinitely many of those. Yeah, and then we will have each single slice is a cylinder. I can add all of the volumes. Adding infinitely many terms is the integral. That means, let's see. Okay, that means volume of each slide will be the cross-sectional area, which of course this one is weird, but we can still try to find it, times the height. Height is the thickness. Now, adding all of them together from 1 to n, I'm adding the sigma, and having a perfect approximation, I need infinitely many of them. And of course, we recognize limit of the sigma is simply an integral. And we need the limits from A to B. Okay, that means now the final thing, the final formula, in order to find the volume, we have to cut it. We have to find the cross-sectional area and just integrate. Okay, that's me just looking at this pink shape. Hopefully the pink shape questions will be better than this one because this one is too fancy. Okay, that means this is, I have, yeah, hang on. Oh, okay. That means to find the volume, we have to just integrate the cross-sectional area with respect to x from A to B. Because what we were doing, we were like slicing the x-axis from A to B. Let me come back for a second. Yes, we can see we're slicing. Always you can think, oh, how can I integrate with respect to x or maybe with respect to y later, but you can always think what axis you were slicing. That's why I definitely slice the x-axis. That means I'm integrating with respect to x. Okay. That means now let's see the first question. That means that's the formula. This is the first one. We do have the second one also in this section. But let's practice this one. Example number 1 should be, but okay. Find the volume of the solid obtained by rotating about the x-axis from 0 to 1, the region under the curve root x, y is equal to root x. That's what we have. We do have a function square root of x, okay, from 0 to 1. Okay, and I kind of looking at this. And now you have to imagine that I'm taking this blue part and I am like rotating with respect to x. Yeah, I'm like swiping around the x. That means I will probably create something like this. Can you see? Nicely, I know it's nice, yeah? That's kind of like a, I don't know, coffee cup, maybe, but lying on the side. Okay. And we just learned that in order to find the volume, we have to find the cross-sectional area. That means I'm taking my knife and I'm cutting. Yes, I'm taking knife and I'm cutting this way. That means you can imagine having a cup and cutting. But of course, this will be the cross-sectional area. And since it was rotation, it's a beautiful circle. I mean, it's solid, that means a disk. Okay? That means the cross-sectional area is just the area of the circle, pi r squared. But we need to find that radius. And we can see this radius, like if this is like some x value, the radius is just the corresponding y, because that is touching the y function. But what we have to do, radius is y. Yes, we can see the same distance as y. But since I have to integrate with respect to x, I have to have the equation for y in terms of x, and of course was given root x. That means that's my radius. Because you can think, if this is 1/2, the radius will be square root of 1/2. If this is 1/4, the radius will be square root of 1/4. Right? That means square root of x. Okay. Oh, I did type y, and instead of y, we have to substitute square root of x squared, which is pi x. And then, yeah, we don't have to really look at this. The volume of this solid will be just the integral from 0 to 1, because I will be slicing from 0 to 1. Of course, integration is telling me that I'm adding everything together. That means I'm adding all of these disks. From 0 to 1, cross-sectional area. A of x is the cross-sectional area. And we did compute pi x. Then pi is constant, x is x squared over 2, pi over 2. Really nice. Yeah, we can see how powerful is this equation. I mean this formula. Okay. That's what we actually doing. And I can tell you that most of the cross-sectional areas will be a circle, because we will always rotate. You can even, probably you read section 5.2, it's just the volume of the solids that are rotating about the x or the y axis. Okay, let's see another one. Oh, a disk, yeah. Okay, now find the volume of the solid obtained by rotating the region bounded by x cubed. We know how function x cubed looks like. The horizontal line 8, y equals to 8. X equals to 0 is actually the y-axis. And the rotation now, the rotation is about the y-axis. That's what we have. We do have x cubed. We have a top limit, 8. And we have the y-axis. Okay, that means this is the only blue part. Don't worry for all of this at the moment. And now we're doing the rotation about the y-axis. You can probably imagine another coffee cup, or I don't know, yeah, a little bit taller, but in different direction. Okay, that's me now. Since I did the rotation about the y-axis, I am afraid everything will be in terms of y, and especially my integration. Because you can even see, in order to get this cross-sectional area, I took the knife on my plane and I cut it this way. That means what I did slice it y-axis from 0 to 8. Okay, we'll remove this one. That means the cross-sectional area, it's still a circle, pi r squared, but now I need my radius in terms of y. That means this is the x distance, is always the other, because it's just the x value. And I have to take this equation, y equals to x cubed, and solve for x. That means will be cube root of y. That's the radius I can possibly do. Okay, that's radius. And it's squared. Okay, don't worry for this one because I'm just writing one of them. We need to jump right away to here. That means now please note the rotation with respect to y, integration with respect to y. From 0 to 8, because that's my slicing, that's my discs, cross-sectional area with respect to y. And I'm just substituting this. Okay, pi is the constant. Oh, I did apply my power formula. And you can even leave it. Let me write a little bit different. You can leave it like that. Don't worry for the values. I mean, we know cube root of 8, but it's fine. I will be happy with this answer. Okay, but the point is on this slide, integration with respect to y. Okay. Okay, I hope it's not too long because I do have one more thing to say. Okay, I really like you that you attending the session. I'm trying to change the times because students ask me, but looks like always the same people. I mean, I know that more students can attend, but if you choose to watch the session later, that's also fine. But please watch it, at least when you know. I'm just addressing to the students that they are not attending live. If you're watching, I mean, if you can't attend, always watch the session. Okay, because it says, yeah, it's telling you a lot. Okay, don't waste any time, let's see. Okay, now this is the last thing in this section. First of all, if we will have, okay, don't worry for this one. I can put R and R. If we will have that shape, like kind of the ring, we know, yeah, do you know the name washer? Yeah, I think it's not really technical. Yeah, washer is actually, yeah, that's the shape, that ring. That's, we have to know how to find the area of the washer. Just in case if we will have the cross-sectional area looking like that. Actually, are you there? Because I'm talking, nobody is even, okay, please tell me if you know the name washer, the name and the shape. Yes, thank you. I'm just testing. Okay, that means we probably know, okay. This is probably from my the next exercise. Actually, I can keep it. Oh no, because you will answer me. That's what we have. We have an inner radius, the small one, and we have the outer radius. That means in order to find the area, I have to take the big circle, pi r squared, the outer, and subtract the small one, the white one. Then I will end up with the ring only. Okay? That means that's how we can find the area, just in case if I don't have a solid disk, if I have the hole inside. That means, let's see this. The region enclosed by the curves x and x squared, okay, it's rotated about the x-axis. Okay, I will integrate in terms of x. Find the volume of the resulting solid. That's what we have. We have function x and x squared. Nice and easy. Points of the intersection, of course, 1, 1 and 0, 0. And now I will rotate this with respect to x. I will take this blue part and rotate. That means you see, because we have empty space here, this will give me, when I rotate, we can see it will give me a hole. That means I still have, actually this one is more like a cup because I have the hole inside. The other one was like solid. That means this is something, right? Like, I mean, that's the resulting solid. But when I take my knife, my plane, and cut it, the cross-sectional area will be just the disk. You can probably picture like a really, really thick coffee cup, and when we will cut it in the middle, we will have a washer, we will have a ring as a cross-sectional area. That means now we still follow the same formula. We have to integrate from 0 to 1 the cross-sectional area. That means now we can see everything in terms of x. That means maybe I can use this one. This will be the inner radius. And the inner radius is touching parabola. That means this will be my inner radius, x squared. The outer radius is touching line. That means this will be outer radius. The cone looks like the absolute, yes, yeah, kind of like, yeah. Kind of like the absolute value the other way, because it's the straight line. Okay, but now on this slide, it's important to notice, important to know what is the value of the inner radius, but we can see the inner radius is just the y value for the parabola, which is x squared. The outer radius, because the line is outside, is the y value for the line, which is y is equal to x. That we can see. We can simply integrate from 0 to 1 cross-sectional area, and we do have pi r squared minus pi r squared, outer, inner, respectively. And if outer is x. Where is my outer? Outer is x. Actually, we do have, I can write it. Outer is x, inner is x squared. That means substituting x squared, I have x to the power of 4. X squared minus x to the power of 4, and pi, of course, was a common thing. And I did integrate 2 pi over 15. But what is important, again, this one. Right? That's the important part. Okay. That means I think, because I do have one more exercise, but I can maybe solve it for you later, or I can do the video, because that's actually, yeah, that's 2 methods, the disk method and the washer method for this section. Okay, and I think we can finish, because I don't want to keep too long because it's not effective, but please check. I will put like a relatively small videos with extra exercise. Okay, extra examples. Do not miss none of them, because I like to repeat them in the weekly quizzes. Okay? Okay, thank you very much for today, and I will put this session and watch for the additional one. Thank you. If you have some question, I can still answer. If not, just enjoy your rest of your day, and of course, keep integrating.